start just with a big thank you. And I do it the opposite way around. Usually thank people in the end, but thank you for being here. Thank you for being here. Thank you to all my lovely, wonderful CMU and CST colleagues. Thank you to my PhD students here who are absolutely amazing, Amir and Nick, and everybody who helped me in this work. So that's my academic lifelong collaborator and good friend, Mohsen Ghaffari, and my other 4 CMU PhD students who worked on this topic. Goran, Ellis, David, Jason, thank you. Harald Recke and Taisuke also helped me in this work. And the biggest thanks, the MVP thank you of this talk goes to someone else. That is my ADHD and dyslexia brain. This talk wouldn't exist without this thing in here. And you know, my brain is wired a little bit different. The chemistry is not typical, it's different. I feel, think, work, do math differently. I communicate. My life is different. I interact, talk, operate differently. And for a large part, I love it. And it's the reason why I'm here. If you ask the doctors, then they will tell you that I'm broken, or at least a little bit in need of fixing, that I have a disorder and a disability. So ADHD stands for attention deficit disorder. Dyslexia stands also, the dys stands for nothing too good. You know, they tell me I need to like become more normal and so that I have less problems in my environment, and that's been society at large, and also, of course, with the last 7 years here at CMU, and they're just wrong. You know, that's just really wrong, and it's pretty sad because even the names are just horrible. I knew that there was ADHD, I didn't know what it was, and it never seemed to apply to me because it really has nothing to do with a deficit for attention. My brain has plenty of attention, it just directs it a little bit where it wants. Math, for example, I can hyper-focus on problems for 8 hours and then realize, oh, I missed 2 meetings, I haven't eaten, and I'm supposed to be at home since 2 hours. So definitely no deficit of attention. And I also think talking about this as a disorder and disability is just not helpful. Here's a different word for different. Exceptional. So my brain is definitely exceptional in all directions, sometimes in a very annoying and painful way, but most of the time in a way that I really like it. That's great. And I also just want to say that to some extent, yeah, it doesn't make it easier. I'm here despite the stigma, despite, you know, some of the discrimination that just happens unintentionally, mostly because people, the system, everything's not really aware, therefore also not designed for people that are different, not very welcoming. But one thing is very clear, I'm definitely here because of my ADHD, because of my dyslexia. I wouldn't be the person that I am, I wouldn't be the scientist that I am without this like weirdly exceptional different brain. And so I want to start with a quick shout out to this wonderfully diverse and different in many aspects family here at CMU. Particularly, you know, anybody with autism, Tourette's, dyslexia, dyspraxia, OCD, all the different cool ways in which our brains can be different. You know, remember, you're here because you're exceptional in many different ways. You're not alone. I'm really sorry that I'm leaving now that I can talk about it a little bit more openly. Stay strong. Be kind to yourself. Be unapologetic in making the world a better place for yourself and for others. Spoken true words from somebody who just apologized. With this out of the way, I'm really excited to talk about algorithms and science and everything. And this talk is basically going to be about optimization, distributed optimization. So computations that happen in large networks or computations that we do on large networks. Okay, when I talk large networks, I'm talking about billions of nodes. So these could either be servers, physical machines that are sending packets around, or these could be data itself, like networks, logical networks that you try to analyze, like the Facebook graph, the internet graph, 3 billion nodes, trillions of edges. Average distance is something like 5. The maximum distance is maybe not 6 degrees of separation, but it's definitely, like 50 or something. And if we work on a network, in a network, you physical-wise, you can only send to certain nodes, but also if you run algorithms on big networks, then just because it's easier to think about and efficient and local and all of these things, typically we're talking about message passing algorithms. So even if it's a logical graph, we're going to describe our algorithms as little ants, as Gary calls it, sitting on this node and talking to their neighbors and changing and doing things. It's just a very natural way of doing things. So this talk is going to be about message passing algorithms and the running optimization algorithms on it. And the kind of formal mathematical model is called congest. It's just what you would think. Like, what is a network? A network is a graph, right? It has n nodes because, of course, it does. The diameter I will write is d. And you only have a local view, right? So each node knows the neighborhood, can talk to the neighborhood, but doesn't know what's globally going on the network. And then typically, if you're talking about optimization problems, you have some weights on these edges. And so I know the weights around me, but I don't know the whole networks. I can talk some limited amount of bandwidth, limited amount of things to my neighbors. Let's just call it login bits just to make it easy. And most of the time, computation is limited by communication. So local computations are fairly free, and the delays and the time that's being spent on communicating is typically dominating in a large order of magnitude. So for now, we're just gonna basically say local computations are free. And now, in such a network, we want to solve our favorite, graph problem, like minimum spanning tree. I want to know what's the shortest path from here to here. How robust is my network? What's a min cut? What is, a flow in here? Like, pick your favorite problem. And we want this as fast as possible. And for all of these problems, pretty clear that, if I want to find out what's the shortest path from here to here, I might have to look at least hop diameter long in the network. Otherwise, I don't even see all the paths. But diameters tend to be small. Think of polylogarithmic or subpolynomial. And so the dream goal would be to have like diameter times some small factors. I'm going to be fairly liberal in saying, polylogs among friends, who cares? This is like, yeah, good. So the dream goal would be order diameter algorithms, right? So let's pick the prototypical problem here that people have studied, just because it tends to be kind of capturing everything that we need. It's the easiest. It's the minimum spanning tree problem. We all know it. Edges on the graph. You want to buy these edges and connect the whole graph. So you're going to buy a tree, min cost tree. Good. In a distributed setting, any suggestion on how would we solve kind of what's the first approach to like minimum spanning trees? Any suggestions? Put ants on the nodes, okay. And then what is the ant going to do? If you have an ant on a node and it looks around and it has different edges, some cheaper, some more expensive.
Take the cheapest
edge. It's going to take the cheapest edge because we all know that's definitely going to be in the minimum spanning tree, right? And more or less, if you keep going this way in the most natural way, you get Borovka's algorithm, right? You start, everything is its own connected components. The graph is empty in the beginning. Every ant is going to walk on the cheapest edge, right? Then you're going to have like some colonies are going to grow, some connected components are going to grow, right? And again, each colony can look in the edges around them, look what's the cheapest edge, adds it to the tree. And very quickly, it's clear. How many iterations do we need for this? Log n, why? Yeah, you're halving the number of connecting components at least, or a constant factor goes down by a constant factor in every round at least, right? So this is going to take log n time, the time that it takes per iteration. And now if a connected component and I want to find out what is the cheapest edge leaving my connected component, I'm just going to collect the information in nodes flooded around in the component. And I'm going to get an algorithm that each iteration I can do in diameter time. And now we have diameter times log n, and we're tremendously happy. Except that I'm lying, and we're not, because there's a slight little cheat here. It's two different, yeah, right? No?
That's the diameter of the tree.
Yeah. So, I said diameter, but it's really two different diameters here, right? The time that it takes to find out my connected component, this is the diameter of my connected component, right? This D is supposed to be the diameter of the graph. It is not true that the diameter of any induced subgraph of any connected component can be vastly larger than the diameter of the graph, right? I mean, here, this connected component, this graph is probably diameter 4 or something. This thing is a long and winding component. A minimum spanning tree can totally look like this, right? So, this is not going to be good. And the best bound that we have on the diameter of a connected component is n. And how this looks, that makes the kitty sad. It's not quite as nice anymore. Okay, good. But what's a good attempt? In fact, to some extent, yeah. We'll see. So, what is known about the distributed minimum spanning tree problem? Like the trivial things that we just did, you can implement it in n log n time. Yay. You can do it in order n time, and that's optimal. And this talk is done. I'm just joking. I mean, I'm not joking. It is optimal, but maybe we should ask optimal in what sense, right? It's existentially optimal with respect to the parameter n, in the sense that for every n, there exists a network in which you cannot do faster than this in the distributed model, and this network is just as a cycle. So if you really want to compute a minimum spanning tree in a cycle in the distributed setting, it's going to take you n time. But maybe if you want to run this on the Facebook graph and n is something like 1 billion, telling your boss that this is an optimal algorithm might not be convincing. It's also D time, yeah, that's true. But the algorithm that we're running is not D log n. I mean, at least maybe it is, but you can't. I mean, it might not be, right? So maybe n is not a good parameterization. D would be a whole lot better, right? So did Garrick, Kutten, and Pelix think. Maybe I do D and n. D they couldn't prove, so they do both D and n, and they got square root of n plus d up to Polylog's algorithm. And again, and this is much less trivial, turns out that this algorithm is optimal. And optimal in what sense? Optimal in n and d, right? So there exists a network which has a small diameter, like logarithmic diameter, right? But n, you can prove using communication complexity that any algorithm that completes the minimum spanning tree in this low diameter network requires square root of n rounds in the worst case, right? Okay, like we got it down from 1 billion or 10 billion to like 100,000. That's a big improvement. 100,000 plus 50. What off? But maybe that's still not really quite good enough, right? And so unfortunately, it's not super clear how to do better. And the algorithmic understandings that you get by getting existentially optimal algorithms is still huge. So over the last 10 years or something, really picked up because the world is getting more distributed. We need kind of an algorithmic understanding. And we have hundreds of beautiful algorithmic papers which work really hard to get the running time down to existentially optimal for min-cut, exact min-cut, shortest path, max flow, Laplacian solvers, you name it, right? And these, again, for these networks, they're optimal in the sense that exists this pathological worst case network, which I can draw to you, but won't. Where in this network you cannot do better, but again, you would probably not expect reality to ever have a network which is this hard, right? So the question is the square root of n network real? Do we have networks that are really, really hard to run algorithms on or to optimize over? Can we define networks to do better? How do we math, if you want to prove stuff, then we need a mathematical model. That's inherently kind of not an easy question. Maybe n and d is also not a good enough parameterization. And again, this is kind of hard to actually prove because how do you model a real net red, or what is a real net redneck? But I conjectured, and to some extent I will show you that there's a lot of evidence and results in this direction that says we should be having algorithms that run really, really, really fast. Like I would conjecture polylogarithmically fast in basically any networks that is ever of interest, right? Yeah. It's not going to be the cycle. It's not going to be this weird pathological worst case graph. In practice, you should have algorithms that are extremely fast, exponentially faster than the algorithms that we currently have. Good. So not the first one to like ask this question. In fact, already in the Gary-Pelek paper, there's basically these two classical questions, which is what graph parameters determine the complexity of distributed of MST, or generally, yeah, they asked it for MST, right? And is there universally optimal algorithm that works as fast as possible on every topology? Right? And okay, yeah, to just make this a bit more precise, there is a graph parameter that captures the complexity of distributed MST. We can call it OptMST. It takes a graph and it tries all the algorithms, and it will tell you the fastest running time is this for this graph. So really what we mean is a nice, understandable, right, maybe approximate description of this OptMST. And then to make this here formal, it's just saying, are there algorithms that for every graph run in roughly OptMST time, right? Whatever this function ends up being, right? Or are there algorithms that, without knowing the network, perfectly adjust to every single network? Are there algorithms that can compete with the best algorithms that's out there, even if this algorithm is specifically designed for this topology that you're running on and that you don't know, right? So a priori, it's super not clear that this should exist, right? I mean, seems, and building it is a completely different question, but it turns out it's, so this is where we started. And over the last 7 years, we basically put lots of pieces together to basically make this happen in some ways. So here's what we can show and prove, that there's a really large class of fundamental network optimization problems, anything that's kind of global and nice, including MST, min-cut, shortest path, you know, you name it. And it turns out that it's super not clear that the complexity of MST on a certain topology should be the same or roughly the same as min-cut, right? I mean, maybe something, min-cuts are easy in some graphs, while MSTs are hard in a network topology of flows. But it turns out that all of these problems basically have the same complexity for every single graph, up to some fudge factors, right? And we can characterize this complexity class, this dependency on the topology, in various different ways. Previous minor density expansion are not tight, but give you kind of one-sided direction. And the new object like hop on its sparsest cuts, make spawn of packet routing, and so on and so forth are actually equivalent characterizations. And some of them I will show you today. And the big intuition and kind of why is the world so nice is because it turns out that the distributed complexity of any of these problems really is equivalent to every single problem, if you understand it correctly, is equivalent to just being able to do a small number, polylogarithmic number of very simple communication problems. So really, all of these problems, the algorithmic complexity in the distributed setting is equal to the simple communication problems, which those I will show you in a bit. Right? Yeah, please.
Quick question, mostly about the model.
Yeah.
So, so we're running like a algorithm at every node, right?
Yeah.
And so are we somehow restricted to be the same algorithm? Like at each node have to be the same?
Yeah, I mean, you have your ID, you have randomness, you have a different neighborhood, you will end up doing different things, right? But like an algorithm is pick, you know, a random node neighborhood, or it picks the cheapest edge in your neighborhood, right? Mark it, takes the marked edges, you know. So, and ideally also we would like here a uniform algorithm, right? So it's one description, which then I load onto every computer and they will compute it too.
No, that's the next question.
Yeah.
You said it's like determined, but if it's like, you know, not uniform, then I suppose the space grows with the size of the graph.
Yeah, but anyway, for a fixed graph, it would still be, the number of different algorithms might still be, yeah, I mean, probably exponential in the size of the graph easily. I mean, this wouldn't be like a nice description, which is kind of exactly the point. You want something that's ideally computable, right? You know, not just some function.
Somehow you're coupling the network and the graph problem, right? So a minimum spanning tree, you could imagine that every node has a copy of the tree and then just computes it separately.
Yeah, but then it wouldn't be a distributed algorithm.
But so the definition of a distributed algorithm is somehow that the network is identical to the graph problem.
Yeah, because you're running kind of, either it is literally the network which you're running it on, right? Or you're running algorithms that are basically written in such a way that you're only working on this network. And there's some, it extends to parallel algorithms and other things as well. I talk a little bit more about it later, but yeah, that's exactly the model. Right? That's yeah. And it's not the only model of distributed computing, right? It's the oldest one. It's maybe, but there are other models that that are equally valid and to some extent maybe yeah, good. But I think we also, this is going to be 7 years of stuff, right? So like, you don't have to get it through it all. Like at any point of time, interrupt me, we can take as long as possible and we just chop a little bit off at the end. So it's totally not a problem, like just awesome. Good, so this is kind of on the complexity side, but I'm an algorithm person, I want algorithms. So algorithmically, we can match this. So we get universally optimal algorithms for, again, like the whole swap of problems up to subpolynomial factors. For nice graphs, where again, we need like proper mathematical descriptions of them to prove stuff about them, but like planar graphs, extruded, minor graphs, and so on, we can get actually D times polylog algorithms for these graphs provably as well. So that's kind of the high level results. And I think they're really important. It's super cool. It's kind of a pretty strong notion of running time guarantee. But also what turned out to be like why I stuck with this for 7 years and why really also I think it has implications way outside of just these questions in distributed computing. Because in the end, it forced us to come up with new tools and think about questions that are fundamental in many different aspects and are generally hard and haven't been as well understood as we would like to. And so there's, we'll see this also, there's many fundamental questions in oblivious routing, routing tables, network coding, metric embedding, online algorithms, new types of expanders that came out of this, that are equivalent to this, that are making big strides in different areas that have absolutely nothing to do with distributed computing. And generally, in distributed computing, you need to communicate over short passes, and you need to communicate over passes that are not too congested, because it's both of them is going to take a long time. And a lot of problems that we know are optimizing L1 notions. A lot of our problems that we know are optimizing L infinity notions. And then the second that you have something that needs to combine both, it suddenly gets a whole lot harder and there's less tools available. And so this whole program really made strides on giving some new like little hammers and things and tools to work with here. And I also try to, and in the end, also, even if you don't care about distributed computing at all, just about parallel algorithm, near linear running times, or all of these things, in the end, the whole thing really shows a clean abstraction and a way to understand, try to understand algorithmic problem from a slightly different angle that really helps in these aspects as well. So lots of big words. Let me try to like actually show you a little bit of the meat that's running underneath. And as I said, there's kind of two natural network communication problems, or there's multiple ones, but I'm going to show you two that end up being kind of really capturing what the distributed complexity is about. And this one, the first one that I'm going to show you is really a bit more natural from the distributed perspective. The second one I'll show you is a bit more natural to you probably if you don't come from distributed computing. But let's start here. So the partwise aggregation problem, we named it that. I'm not sure if it's a great problem, but it's basically like it's a natural version of like the simplest version of distributed divide and conquer, right? So each node I give a value, then I partition the graph into node disjoint individually connected parts, right? See, and then I just want to compute the simplest, I mean, they need to be connected, otherwise I can't run a distributed algorithm on them, right? And I want to just compute the simplest thing, some simple function on each of these connected parts, on each of these subnetworks individually. And this should kind of sound familiar. Have you seen this before? Yeah, this is exactly what we were asked to do. Like here, every part is every connected component is a node disjoint connected part, right? So it might be really long and windy. And for each of them, we'd want to compute the minimum value. Every node knows the outgoing edges, right? I just want to compute the minimum of this very simple aggregation function, right? Just the minimum. And that's exactly, so it pops out very naturally, and you can think of it as divide and conquer. And it turns out not any algorithmic problem, but any of the algorithmic problems that I've said many, many times, you can reduce to basically minor aggregations in a minor, or in these connected parts or connected components, or however you want to talk about it, right? Part of this aggregation problem, very, very natural. The other one is many different names. I don't know, point-to-point communication. It's just TCP/IP. It's like I have a network. Here am I with a packet, SI, source SI has a packet or has some information it wants to send it to some other node in the network. Here's another node that wants to send it somewhere else, right? And I have many of these point-to-point connections, and I have some amount of data. Let's think of also, just for simplicity, like log and bit value. I want to communicate this value from here to here, right? Doesn't get a whole lot more natural. So I'm gonna call this peer-to-peer, like P2P, point-to-point routing. In information these are called multiple unicast, but you know, whatever you want. And simple problem. Here's kind of generally, of course, how hard is this problem? Well, the more data I have to send, the harder it's gonna get. So here's kind of, it's not really, you know. So here's kind of a simple and useful kind of restriction to it. I say I have point-to-point connections where it is possible to connect every source to every sink via a no disjoint path. Can be a really long path, but it's possible to connect them, so I can't send too many things, or I can't send too many things over a tiny cut or whatever. So this disjoint point-to-point is just any instance where the SI and TS is possible to connect S1 to T1 in a long no disjoint path. Okay. And here's kind of a cute little observation. These two problems up to polylogs are really kind of the same thing, right? I guess the interesting direction is the following, right? Or maybe let's start with the easy direction. Like, why is the point-to-point harder or like not easier than part-wise aggregation? Well, because it could simply be that my parts are long disjoint paths, right? That's a possibility. And then part-wise aggregation says aggregate everything in there. And we are just saying, oh, I make it easier to you. Just let the 2 points at the end exchange information or compute and aggregate, right? Good. On the other hand, suppose that you can do no disjoint kind of point-to-point aggregation. And now you want to solve the part-wise aggregation problem, which is like a more complicated set. How are you going to do this? You're going to compute a spanning tree of your connected component. You're going to do a heavy light decomposition and just decompose it into log and pass into passes, such that from anywhere to anywhere you have log and only have to traverse log in many passes. And now you're back to basically the special case where you have a pass and everybody wants to be informed. And so you just do divide and conquer. You first send it to the middle. From the middle, you send it, you know, to the quarters. From the quarters, you send it to the eighths. And you know, log n for the heavy light composition, and another log n for the divide and conquer. And log squared many steps, you can solve part-wise aggregation with point-to-point communication. Good. So, you know, up to polylogs, which again, I'm going to drop all over the place. These things are really the same problem anyway, in their worst case complexity. Good. And the claim is that basically your favorite optimization problem, unless it's like all pair shortest paths, which requires a lot of information, which takes a lot of time to compute or whatever, like most of these classical optimization problems, the complexity is exactly up to polylogs going to be as hard as doing this type of communication. Right? This really captures what's going on. Good. Now, with this claim out there, we can just write our kind of universally optimal MST algorithm. Very simple. So the high level idea is, if you've seen Borufka, basically takes minimum spanning tree and reduces it to part-wise aggregation, right? Log in many of those. We know that we can solve part-wise aggregation with point-to-point, right? As we just said in the last slide. And then now we just still need to route point-to-point, right? So how do we do routing in the internet? We need to find passes, a path from here to here for every, you know, for every node. And what would we want from these passes? We want them to be short, because otherwise it's going to take a long time to send it along these passes. You don't want them to be too overlapping, like every edge should be used by at most congestion C, this for a small c, many passes. And then once I found these passes, routing, then I can schedule how to send them along, and that's really easy. There's this classical result by Leighton Maxwell, which says you can actually do it in order C plus D time. That's not so easy, but since we're willing to do it randomly, you just, so the simplest thing is you just take a random delay and then let the packet run, and that just works, like in C plus D times log n. Really, really easy. Good. So the total algorithm looks like this. You start again, every like it's an empty tree. Every end is in their own little node. For each connected component, we want to find the cheapest edge and add it to the tree. How do we do this? It's just a partwise aggregation problem. The partwise aggregation problem we reduce to log squared many kind of you do a heavy light decomposition of the spanning tree for each component and do this little divide and conquer. And then every peer-to-peer, point-to-point instance, we've tried to find approximately shortest and lowest congestion passes, right? And then schedule them in the trivial way, okay? So this is the only part, really finding these passes is a part that's still hard, or that's definitely highly non-trivial. And so the total running time is just going to be log n times, or log to the 3 times, I suppose, of like runnings and doing the minimum time that it takes to actually do a communication with anything that's disjointly connectable, and the time that it takes us to construct these routes. Right? So if you can do this fast, then you're going to be as fast as the routing problem. And I was claiming that that's as fast as you can be. Questions about the algorithm? If I move on. Okay, good. Now, so here generally is kind of how do you prove that an algorithm is universally optimal. There's 2 parts to it. It's the upper bound part of construction of the algorithm and the lower bound part of saying you can't do any better, right? And the upper bound part generally is you reduce a problem to partwise aggregation, right? In MSTs, it's super trivial, straightforward, and Borufka gives you this right away, right? So this is problem specific to other problems. It's much, much harder, and this is where your understanding of the problem and the whole ingenuity and the last decades of work went in there, and we just take it and say, this, we understand the problems well enough to do this. Everything like Laplacian solving can be done in a very small number of minor aggregations, partwise aggregations, right? Good. And then for the algorithm, you still need to solve this fast. And so basically, what does it mean to solve it fast? You need to get approximately optimal packet routes in time that it takes to then send them in the end, right? So this is the non-trivial part, but it's the same for all the algorithms. And maybe I have time to show you a little bit about how to do that later. Huh? The first part, problem specific, just reduce it to partwise aggregation. The second part, kind of pretty generic. Okay. On the lower bound side, we want to say that this algorithm, this MST algorithm that I gave you, is as good as it can possibly be. There's no algorithm that's faster up to some fudge factors. Okay. 3 parts to this. One is, again, problem specific. You reduce this problem to a simpler problem like connectivity. You say, fine, like if finding the MST cannot be done faster than giving me a subgraph and deciding is it connected. And that's typically trivial. I mean, I'll give it like really high edges, really small edges. If anything that's not there, really small, high weight. Now, if the MST is expensive, then clearly you can't just build it with a short, connect it with a like low cost edges, otherwise not, right? And these reductions are basically, for all of these problems, they're very straightforward to connectivity. Typically, many of them have already been done for these like square root of n plus d lower bounds. They also reduce to connectivity. Good. And then I need to show you that actually there's 2 parts, and one is actually a bit surprising. I need to in the end, I need to let's start here maybe. I need to show you that also it's going to take at least it's as hard as connectivity, right? But also connectivity needs at least kind of this communication amount of time. And this is done with reduction from communication complexity. It's the same kind of technology that underlies the square root of n lower bound. The one thing that makes it trickier here is in the classical lower bound, I can design this really nice graph, which has a really nice structure that helps me in my proof, and then carefully embed my my communication complexity, my disjointness problem in here. Here, I want to prove this for every single graph, right? I have no idea what the structure of this graph is. I don't have any like proper description. I can't, this is a graph that's just given to me. And so I need to somehow show that I still can find a way for every single graph to embed a large enough and complicated enough communication complexity instance to relate it to this partless aggregation problem. Okay. The second part here, or this part here, is actually a bit trickier because, and maybe if you haven't seen it, a bit unusual. So we're saying the partless aggregation problem saying, here's information, I want in the end that this node knows this information. Right? How are we gonna solve it? Well, more or less the only way is that intuitively in the beginning, or like if you went 10 years back, like people thought the only way that you can solve this, you take this information as a packet, you send it along a path, maybe you copy it, right? Maybe you like split it into 2 subpackets or whatever, you send it along and eventually it has to arrive there. And it's kind of like a banana, you know, like a physical quantity, you send it through the networks, you route it, right? But if we want to claim that there's no better way of solving this problem, we need to prove that there is no, like this is the best you can do. If this takes a long time, everything needs to take a long time, right? There's no weird way of coding things together, XORing, doing whatever crazy stuff you can imagine doing with information, which does it faster. And that seems obviously true, right? But it's not true, right? And in essence, what we are saying is coding cannot help. Coding within the network cannot help, and that's inherently kind of something that the information theorists call a network coding gap statement. Like the gap between routing and coding is not too large or not existent, right? Coding cannot help too much. Kind of surprising to see it pop up here. And this is something that has been kind of in the information theory community, has been developed, kind of the fact that you can do sometimes better, and trying to understand this has been developed in the information theory communities. It's a whole area now that's network information theory. And in fact, more or less, it's very similar to the question that we are asking here, right? How much can it help in peer-to-peer transmissions? How much can it help, and if it helps, how much? It's very, very close to the biggest open problem in this area, which is called multiple unicast conjecture. So what they say is that if you have an undirected network and you have point-to-point, exactly our problem, point-to-point communication, then the conjecture is this cannot help at all. Nothing, not at all, to increase the throughput. Okay, and turns out that an order log n gap of this can help at most log n. That's known, and it follows basically from the multi-commodity max flow sparse cut gap. And in fact, nowadays they couldn't prove it, and then it sounds that we're doing things conditionally, and now actually we are at a stage where they can prove that if you could prove anything better than this order log n, like just tiny little bit of log n, it would imply a circuit lower bounds for like multiplication. I mean, it's a really, really hard problem. Huh? Good. We are asking a slightly different problem, right? This is going about throughput. We are asking about a more strictly more general problem. Throughput is basically just large number, or if the data goes to infinity, how much time is it going to take, right? And there it doesn't matter over how long of a path I send, because it's going to cause a delay, but then a pipeline. And as the data goes to infinity, the path length doesn't matter, right? So it's an affinity statement. We are asking about an affinity plus a one statement, right? And so here, it turns out that actually we can prove that coding can help, but luckily it cannot help too much, right? We can give you some examples where it takes actually polylogarithmic, small polylogarithmic factor faster if you code, but log squared, not more than log squared, so that still makes us kind of happy. And what I could find out is that these are the first type of network coding gaps for completion times instead of just throughput. And this, some of this proof was really inspired by stuff that came from the distributed computing community. This like square root of n del Sama type lower bound. It's really kind of a lot of inspiration came from distributed computing into now information theory and back. Anupam.
So you're showing a coding gap. Right?
Yeah.
You just said coding gap is super hard.
For throughput. I mean, they're still not easy here, but then they turn out to be not. It's a more general problem, which means actually the upper bound, to some extent, is the lower bound is harder, right? In fact, here it's impossible to prove, right? And here we can prove something. The upper bound is actually harder, right? Because we're saying even in this, even if you take delay into account, it's not gonna, it's not. And here's actually, so I have the example. So we're just saying coding cannot help for distributed computing. I mean, not much, it can, but not much. When we talk about round complexity, turns out actually coding can help for message complexity in MST and distributed computing. So it's also even there, like can help a lot, polynomially much. Even there, it's not a, you know, it's not such a weird statement. So here's the thing, in undirected graph, point to point, you cannot do any better. Here's, just to give you kind of a feeling of these weird things that happen, right? Here's an example where you can show that at least a constant, like you can do things here faster with coding versus routing, okay? Very simple example. And we have a bunch of nodes, 5 pairs here. This one wants to send to here, this one to here, this one to here, and so on and so forth, right? The graph here is basically a complete bipartite graph. Every edge is actually a path of length 3, right? Yep, black edges, path of length 3. Complete bipartite graph, except there's no direct connection from S1 to T1 or from S2 to T2, right? So the one person that I really want to talk to, unfortunately, there is no fast path. In fact, the shortest path, well, yeah, right. So then everybody in S is connected to this one node, and everybody in T is connected on this one node, and there's one kind of short one length one edge here, right? So now, if I'm S1, I want to send to T1. There is a short path from here to here, length 3 path, right? I could use that, but everybody wants to use this, right? If I don't want to overload this edge, what can I do? I can send it to the other side and maybe like on one of these edges, right? I mean, the shortest path after I delete this edge between S1 and T1 is length 5. And that's true for every single node here. So either everybody routes their message to this one single thing, and in this case, there's 5 nodes, there could be more, right? It's gonna take at least 5 times to like send one packet per time over. Or at least one pair is sending not on this edge, and then the shortest path that's available is length 5. So clearly, you cannot solve this communication problem any faster than in 5 rounds. Impossible, right? Except you can, but you can't do it with routing. Does anybody happen to see, I mean, no network, enough network coding to see Haresh, maybe? No? Yeah. It's, I mean, if you have never seen it, it's just weird. Yeah, cool.
The XOR of all the S's through around, and then every other node except S1.
That's right. So every node here in length 3, these passes are all disjoint, right? I can send, everybody can send their messages to everybody except the one person that they want to send it to in 3 rounds, no problem, right? You just send it from here to here. Now, everybody knows every single information out there in the world except the one single login bit that it really wants to know, right? And then we do exactly what you said. Everybody also sends the information to S. S is going to take all of these login bit values, XOR them together, and sends the single login bit XOR string to T, and from T to everybody. That also takes 3 rounds. Now you know all the information in the word except for the one thing that you want to know, and you know the XOR of everything. So you XOR it all together, and magically it just pops out, right? This one piece of data that's being sent here, it's not like a physical quantity. It's like it's a mixture of a banana, apple, and an orange, where if you have an apple and an orange, it becomes a full banana, right? If you have an orange and a banana, it becomes a full apple. It's not just a third of each of them, right? This is something that information can do that flows and quantities cannot do, but turns out that this can help, but not too much. So we're fine. Awesome. So here's another kind of interesting question that people have really looked at hard, and kind of something that turns out that more or less the question that we're asking it is directly asking about this completely separate weird question in a completely different field. Directly, basically, is peer-to-peer routing, point-to-point routing people have looked at, right? But here, we want to do it distributedly, right? So nodes don't know. If I know I want to send from here to here, I don't know who else wants to send stuff, right? I don't know the network traffic. I also don't know the network topology, right? So this, and then the algorithm is going to be potentially, it's a constant degree graph, right? It's going to be really fast, polylogarithmic time. How much information on each edge you learn per round, log in bits of information. The total amount of information, the whole running time of the algorithm that you can ever learn about the world out there. It's polylogarithmically many bits. The amount of to describe the whole demand that's out there, who else wants to send the network traffic, that's order n bits. You basically know nothing in the beginning, but also over the course of the algorithm, you have no chance of learning who else wants to send where. And you can't really easily adjust getting out of the way of everybody because you can't learn where everybody wants to go, right? So not provably, you need to be oblivious, but intuitively you learn next to nothing. You still need to figure out how to get my packet from here to here. So, you know, you might want to have to do it. You might have to do it basically independently, which is called obliviously. Everybody chooses a path obliviously from all the other demand pairs. Classical question, oblivious routing. And this has kind of been solved, but again, only for the congestion only problem. It's a very beautiful result. It says that you don't need to know the network traffic. I just, you know, you tell me where you want to go in this network, and I give you a distribution of passes. If everybody samples from their distribution, then you're lock and close to being optimal for every demand, right? In congestion. But you might have a very short demand that with these record trees becomes really, really long. And in special graph topologies, you can do it. It's a big open problem. Kind of people thought that you shouldn't be able to do it, but it turns out that you can. And so basically what's one of the parts that we kind of proved was to say that there's these hop constrained oblivious routings where you tell me, I want to be competitive with the best passes of length 100. Maybe I don't route it over length 100, but you know, 200, or like in asymptotic terms, there's going to be polylog losses in both congestion and dilation in the length. But I give you a distribution for any pair that's like close enough. I give you a distribution. If you independently sample from this distribution, you're competitive, right? And the way that this works is to go through tree embeddings. Anupam has done like lots of beautiful works here. Any metric, you can basically pretend that up to a log, in fact, it's a tree. That makes life tremendously easier. If you talk about hop constrained distances, they're not a metric. They're very far from being a metric, because just because there's a 10 hop path of length 100 here and a 10 hop path of length 100 here does not mean there's a 10 hop path of length 200 from here to here. In fact, there might not be a path at all, right? And turns out you can still get these like beautiful tree embeddings for at least relaxed versions for these non-metrics, and put them into this proof and get something cool out. And then let's see. Yeah, I have 5 more. No, I have actually 10 more minutes, right? Yeah, no, 5 more minutes. Okay. Yeah. So this basically, if I know the network topology, I can write down this distribution over passes, right? And not be too far off. So if the topology is known, then we're good. But here we also want to find these passes fast and distributedly, right? So I can't run these Recke oblivious routing type things in here. And the problem is that even so compact routing table, okay, so if I have a fast algorithm, distributed algorithm that in the end figures out how to compute these distributions, because a node learns very little information during this fast algorithm, I can write all the information into a routing table. I can know the node puts the information at this node, and any distributed fast construction of an oblivious routing will therefore also immediately give you a low storage routing table that just after you've stored this information, you know how to route packets, right? And that's a really, really cool thing. But the problem is, even in the just single congestion case, you have existential results for these compact routing tables. We don't have fast distributed constructions. And all the near linear time sequential algorithms of these things are building on expander decompositions. Right? So expander decompositions are this really, really cool, powerful thing. And expanders, everything is easy, right? Routing over random paths, like expanders are just great. And expander decompositions are this kind of nice thing where you can say more or less, you know, every graph, I can cut a few edges, like leave only a phi fraction of edges between clusters, and every single component is a 1/π expander. And then you contract them, and like inside, you know what to do, you contract them, you reduce the fraction of edges by a factor of phi, and life is great, right? And so this is kind of how these routings in the end work, even just sequentially, not even distributedly. The problem is that if you contract a 1/π expander, and then just pretend that you can route in one hop through this expander, the length of the path, right? This one hop path through this no contracted node really needs to be routed through the expander, and the length of this path is the diameter of like a phi expander, something like 1/π, right? So every time you remove a phi fraction, you remove everything but a phi fraction of the edges, you're also increasing the path length by 1/π. By the time that you've reduced it all the way down, no matter in how many small steps or not, you have order n long passes, right? So it turns out you can't just do it with regular expanders. So you need this. So we came up with this like new notion of small hop expanders, where within this expander you can route over short passes, even shorter than 1/π. And turns out these exist. In fact, I can give you some examples. In fact, so the definition more or less is do I want to go in this 5 minutes? Maybe quickly. Okay. So I'm going to show you how these kind of new expanders look like, in a very fast way. So expanders they're not defined this way, but equivalently, I can characterize them up to polylogs, saying that what is in a phi expander? Every single unit demand where every node sends only degree much stuff, receives degree much stuff. I can route with congestion 1/π. Up to logs, it's exactly an if and only if statement. You're a phi expander if and only if this happens. The new definition, it's not really the definition, but the new definition of an h-hop phi expander is saying that if any unit demand, okay, it should be a unit demand that's close by, otherwise, you can't route it over short passes. But if you're asking me to route between close together nodes, and you can route them over not too much longer passes, like 2h, with congestion over phi, I say you're an h-hop phi expander. And h can be much, much smaller than 1/π. Right? Here's some example. Turns out that the line, really bad expander, it's a 1/h h-hop expander, right? If you only want to route between two nears, how much congestion can you get on an edge h? That's great. Great expanders, right? If you take two cliques, connect them with an edge, not a good expander, right? I want a bunch of information, like there's a bunch of pair I want to send from here to here, they're all close, right? Now I want to do this together, this edge is going to be really badly congested. Makes this pass in the middle longer than h. Great h-hop expander. Right? Why? Because locally it's kind of looking like a lollipop, or like a pass, or a lollipop. Right? There's no information that could possibly be sent from here to here. Any information that needs to be sent from here to here, if it's unit demand, is fine. Anything sent in between here, it's fine. Anything from here to here is fine. Anything within the clique is fine. Right? So you can define a whole theory of h-hop expanders. You need to have fine sparses cut, which relates to this network coding gap kind of things that I showed you earlier.
Should I view this as just saying for every vertex, if I look at an edge neighborhood, that is an example. This holds true for everyone.
That's not completely true. It's kind of like for every neighborhood, you can embed a scale down in terms of capacity, like 1/π scaled down, h-hop expander in the neighborhood, but also the congestion of many of these overlapping expanders shouldn't overlap too much. That's a much closer to like, yeah. But it's, yeah, that's kind of, but it's pretty close to what you said, right? Yeah. Good. Lots of cool new stuff. Think these in particular will be very useful in like a host of other problems that have nothing to do with distributed computing, anything I talked about today. Is that generally this framework of reducing things to part-wise aggregation to minors or whatever is a really good way of thinking about problems. In fact, once you can reduce it to something like this, you have understood the problem in a new way, and you automatically typically get near linear time algorithms, parallel algorithms, semi-streaming algorithms, any model in which you can kind of apply this part-wise aggregation. And so a few things that we could do, for example, even just deterministic parallel, near linear time, polylog depth, shortest path, pretty fundamental problem. We solved basically by going through this problem like slow thread spanning trees, randomized to deterministics. The first one comes through this kind of framework. Embeddings, stream embeddings, Bourgain's embedding, lots of kind of fun stuff. Thank you for being here. Thank you for this fun time and good stuff. Here's kind of a quick summary of what we said. Universal optimality, basically all of these fundamental problems are basically equally hard because they can be related to the simple communication problems. You get these new algorithms and lots of kind of new tools that like address L1 and affinity type of notions. A nice new framework of different perspective on graph algorithms. I'm here for a month. If you want to talk about anything, neurodiversity, life, optimization problem, distributed computing or whatever, I'm 7:05, like swing by. It's been a true pleasure. Thank you.
So your new low-thread spanning tree algorithm is basically overlaying distributed computing on top of the old algorithm, or it's a new algorithm?
It's basically an old. I mean, it's following an old template. An old template of known construction of minimum spanning trees. It's using your exponential start time routing in between as a thing. The problem is that in order to do the classical route, you need exact passes. The exponential start time clustering breaks really, really badly once you have even just 1 plus epsilon approximations in many ways. And we don't know how to do exact distance computations in parallel fast. So the main problem one thing was to even get approximate distance computations to be fast. That's Jason did this, we did it to be in a deterministic setting. But then the biggest problem with low thread spanning trees is that you need to find a way to compute them without, while only relying on approximate distances. And that's where kind of all the cool new stuff happens and where this kind of also helps. Yeah, I'm happy to like show it to you on paper more. Yeah.
Yeah, just out of curiosity, like how big concretely are the polymorph factors you're talking? Like, do you get like actual practical algorithms or?
Okay, I mean the analysis is, at some point you're just trying to make your life easier and you're not optimizing. So if you would just, most of the time we don't keep track of it. Although for different problems now, like MST and MinCut might not have the exact actual complexities. It might be a log factor of. Like connectivity and MST could very well be a log factor of, right? So it's not even, then you need to like be more specific. No, no, it's not that bad. Definitely not. I think in the end, you will probably not run this like straightforward oblivious routing with like good asymptotic running times as a primitive, right? Likely anyway, you have some kind of routing, some way of sending packets already implemented in your network, right? You're not gonna necessarily do this. Also, and then if you run kind of, let's say, for example, Borufka, with a slightly optimized version of like doing this routing on top of it, yeah, it should be fast. Like the analysis will not give you the tightest constants in front or in the exponent. The algorithms should be decently practical. reality also, no problem, is as clean and simple as our like exact max flow algorithm, right? In reality, the input is nicer, the networks we can choose or are nicer, the problems have more constraints. So usually I just think is, you want to understand the problem better. Once you understand, and kind of asymptotic running kind of questions, asking them really helps you to have a benchmark for how do I, typically there's many near linear time algorithms that will run slower in practice if you implement them directly out of the paper. That might be slower than the quadratic time algorithms. But if you have a near linear time algorithm, I feel like you understand the problem a whole lot better. If you take that understanding, not just the paper itself, bring it into an algorithm, even just a heuristic, might not be, provably fast, then you definitely, like, understanding will in the long run definitely make a difference. It's a great question. And it's always like, you want to work on models that are clean and nice, where you can ask fundamental questions and answer them in a provable fundamental way, but you also want to stay close to reality, and it's always. Sorry.
No, I mean, I like that, if you have like maybe the right perspective, usually like the algorithm will also probably be,
it becomes much cleaner, yeah. Both in the kind of theoretical description, and then also like, that's why you have these interfaces, right? I mean, you could just say implement it however you want, but MPIs is like node-based view or something. It really, like, it gives you a guideline how to express yourself in a way that's then automatically also parallelizable and so on and so forth. Great question. Any other question?
So what are like the performance?
So lots. I mean, some of this is, so I think the tools actually will extend, like age of expanders. We just kind of, came to it through this one, and since they have much, much broader applications. If you ask me, probably, min-cost floor algorithms, parallel ones in 5 years from now should probably be based on similar things, like expander decomposition generally. Like, they're old, but they're really kind of, we have only recently discovered of how powerful of a tool they are. There's other problems that I want to understand from this point of view. There's actually big fundamental barriers that pop up in many like parallel or shortest path algorithms to go beyond sublinear, right? I mean, here sublinear overhead. I mean, you're improving over n is like square root of n, right? Anything that's subpolynomial is going to be a ginormous improvement, right? But in the end, it should be polylog, and it should be like proofs from the book with more polylogs. And there's still many. There's really trying to go this way also points to a few like very fundamental problems that can pop up everywhere, and there's a good bunch of those to still like really understand. So it looks like it's kind of done, and maybe like the big framework is done enough to like state it as a result, right? But is it in a place where we like really understand it? No, long not. And there's many, many interesting problems here.
If there are no more questions, let's thank Bernhard.